let's continue our history lesson. Let's pick up where we left off in 1925 with Erwin Schrödinger. That's an umlaut over the O, so you pronounce it with sort of a guttural tone to the vowel, so it's Schrödinger, although we can just say Schrödinger. And here he is, a pretty happy-looking guy. He developed a new model called the Electron Cloud model. It's completely different from the most recent Bohr model of the atom. In describing it, he wrote an equation to help figure out the probability of locating a particle at any given moment in time in the atom, in this case, right? And this is what the equation looks like. You do not have to write this down. It's way beyond the math that we do in this course. There's no reason to know it, but in this is this symbol here, which is the Greek letter psi. That's called the wave function. It's a measure of the probability of locating a particle. And that's the idea, is that every time you want to know where the electron is in the atom, it could be a certain probability it's going to be there. So let's look at a visualization of that. Okay, so here's sort of a three-dimensional cutaway view of the atom. Right here is the nucleus. You can see that's shown here. And these little red dots, that is representing the electron at any given moment in time. So imagine you were to take a snapshot of where the electron is at successive moments in time. And so each one of those is just a momentary photograph of where it is at any given time. And you notice that according to this wave function, according to this probability equation that Schrödinger came up with, it's all over the place. It's not just going in a circle of a particular radius, an orbit, an energy level, as Bohr predicted should happen as long as angular momentum is quantized. So this is very confusing, and yet this actually agrees with reality. It agrees with experiments. That turns out you can actually find the electron at all different locations within the atom. It could be in its usual orbit, it could be all the way out there, it could actually be in the nucleus. The probability exists that it could be inside the nucleus. Now, here I'm going to click on this where it says Electron Cloud, so it's sort of going to freeze these snapshots in time. You're going to see them build up as what's called a probability distribution. It's the same picture as before, except we're sort of freezing all those moments in time and overlapping them, superimposing the image of where the electron is at any given moment in time, so we can see where it most likely appears to be. And you can see it's forming this hazy sort of cloud, and the vast majority of them are right here. And this is why we know that Schrödinger's idea works, because it turns out that the place where the electron is most likely to appear exactly matches the Bohr radii, the electron orbits that Bohr predicted. So even though it's a different model, and it's not giving exactly the same information as Bohr, the most likely, most probabilistic case of finding the electron agrees with what Bohr said. But this really is a completely different view of how we picture what's going on inside the atom. Again, this probability function says that there's a certain probability of the electron being literally anywhere inside the atom. You can actually calculate there's a certain probability it's going to be inside the nucleus, which doesn't make a whole lot of sense, except the probability exists. It's just the probability is really, really low. There's also a probability that the electron in a particular atom is not even inside the atom. It's one atom to the left, or in a completely different object, or halfway across the universe. So you can calculate this probability. It's just that those probabilities are ridiculously small. But they do exist, and this is the weirdness in this part of quantum physics, what we call quantum mechanics, that everything really is based on probability. Now, Einstein himself hated this idea. He had a very famous quote. He said, "I do not believe that God plays dice with the universe, that everything is a matter of chance, except this new view of the universe, this quantum mechanics, is actually our most successful way of describing the universe and making predictions." All right, so now we're going to go to Heisenberg. There's a picture of Heisenberg in his youth, and I always thought that Heisenberg looks a little bit like Biff Tannen from Back to the Future. McFly! Right? Isn't there a resemblance there? Alright, so here's Heisenberg's contribution, his uncertainty principle. Here it is in equation form. We can write this down if you'd like to. Here's Planck's constant again, just showing up in all sorts of places, right, which is why it's so important. The deltas here represent an uncertainty. So this is the uncertainty in an object's position and the uncertainty in an object's momentum. And it's saying if you were to multiply the uncertainty in the position times the uncertainty and momentum of any particular object, there is a lower limit. And the lower limit is h over 4 pi. That's saying that you cannot know either of them, either the position or the momentum of an object, to infinite precision, because there's always going to be the other one to counterbalance it. So to help you visualize this, let's say you have a particle moving around inside an atom. You want to know where it is at any given moment in time. So to know where it is, you've got to sort of trap it. Now, when trapping it, you'll have a lot of information about where it is. Be very certain in that, but you really don't know how fast it is moving because you trapped it. You sort of stopped it moving, so maybe you knew where it was going before, but at this moment you don't know how fast it's moving, so there's a lot more uncertainty in its momentum. Let's say you want to measure its momentum, right? So you track it and you find out how fast it's moving and you know its mass, you can calculate its momentum to a pretty high degree of precision, but in doing so it's moving, which means you don't know where it is at any given moment, and so there's a lot of uncertainty in its position. So that's what Heisenberg's uncertainty principle is saying. Another consequence of the uncertainty principle mixed with Schrodinger's idea is that you can make all these predictions as to what an object is doing, except that there's all these other probabilities, which means there's always the probability that it's going to appear, it's going to happen in some other way. Maybe it's not going to be the most probabilistic outcome, and you won't know what actually happens until you do the experiment. And so until you do the experiment, it turns out all probabilities exist. And of course, this is the very famous idea of Schrodinger's cat. The story goes that there's a cat in a room, and inside the room there's also a radioactive isotope that's ready to disintegrate at any given time, and in doing so it's going to release an energy radiation that will kill the cat. But you don't know when it's going to do it. And so there's a certain probability that it has already happened, and a certain probability it hasn't happened. So with the door shut and no information about what's happening inside the room, you don't know whether the cat is dead or alive, because you don't know whether the isotope has decayed or not and killed the cat. And so until you open the door, the cat is in both states at the same time. It is both dead and alive because you don't know which it is. And this mimics the idea that until you've actually done an experiment, you don't know what the outcome could be. You know all the outcomes that could happen, but until you actually observe it happening, it hasn't happened, so you can't isolate that one particular probability. So it's in other words, it introduces a whole lot more weirdness into this idea. Okay, so let's continue our historical study. As technology progressed, as we knew more and more about the atom, scientists found more and more particles. As they developed more and more larger and larger machines to smash things together, they found more and more things coming out. And so they started making lists of all these things. And so here's a list of some of these fundamental particles. Here's the electron, here's the positron, here are those neutrinos we talked about, here's some other things called muons and other neutrinos, other things. And don't worry about all this information, just it's properties of these objects. And as technology progressed, the lists got longer and longer and longer, and it seemed like every single thing that scientists found was another fundamental particle, but that didn't seem to make any sense. It came to be known as the particle zoo, because it's just like a wild menagerie with almost no rhyme or reason. A very famous quote about this was from Isidore Rabi. He said, "Who ordered that?" As in, who made a universe where every single one of these things is a fundamental particle? And it became clear that that wasn't true. These weren't all fundamental particles, and so they found that there were patterns, and they actually broke everything down, and things fell into more categories as they realized the similarities and the overall structure. And here's the overall structure, what's known as the Standard Model. And so it seems like this is our best version of matter right now, that all bits of matter break down to these particles. There are the quarks, which are given the fanciful names of up, down, charm, strange, top, and bottom. A lot of these were discovered in the 60s and 70s, if you catch my drift. And then there are the leptons, the electrons, the muon I mentioned before, neutrinos, these other particles, and there are also antiparticles, every single one of these. And so we're pretty sure that these are the fundamental particles, the tiniest bits of matter in the universe. We've been wrong before, but there's a lot of evidence that really all matter is formed from combinations of these particles in different arrangements. And over here are the force carriers. With our fundamental interactions, there must be something that would transmit the information. So the photon transmits information for the electromagnetic force. These W and Z bosons transmit information for the weak nuclear force. There's the gluon, which transmits information for the strong nuclear force. And then, most recently, we've discovered the Higgs boson, which is what we think gives things mass. Now, this was discovered with the Large Hadron Collider. Here's an image of the Large Hadron Collider, shown head-on. Yeah, this is a very, very large object. Down here is the path of the objects. They would go in this way, and around here are magnets that cause these charged objects to go in circles. Here's a sort of a map view of it. There's really two circles. Objects are accelerated here, and they're accelerated at very fast speeds by magnetic fields, and they crash together at different locations around the circles, and there are detectors there to see what happens when they crash and come out. Just to give you a sense of scale, this is 2 miles, right? This is a very large collider, billions and billions of dollars. This is an image of the first collision. 2 protons, or streams of protons, I should say, from 2 sources, collided here, and each one of these yellow tracks is the was left behind, some of the things that came out here, different particles that smashed together. Here's a more of a three-dimensional view. Each of these yellow tracks is a particle that came out from these collisions, traveling a different arc, a different path here. And the Large Hadron Collider was able to produce tremendous amounts of energy to speed these things up and crash them together to see what's inside. It was here documented from an XKCD webcomic. Okay, maybe not in the best sense of humor, but the point was that there was so much energy in the Large Hadron Collider that when scientists turned it on, they weren't sure if it was going to be safe. In fact, there was actually some evidence that when they turned it on, the Large Hadron Collider would actually form a black hole that would then kill us all. They turned it on anyway. They poured a lot of money into this thing, and turns out we were fine. We did not create a black hole. But the point is that they're still trying to find things, and the Higgs boson completed a piece of that puzzle. We think the Higgs boson, or maybe a Higgs boson, maybe we haven't found the right one yet, is going to describe why things have mass, which brings us back to this picture, the standard model, that now we have something that may tell us why things have mass, which is great. But this here is rather important. This is the 4% of the universe we know about. There's other things we don't. That's what the blank space is over here. Here's the stuff we don't, and there's a whole lot more that we don't know than we do know. For example, dark matter. It seems like there's a lot of stuff out there that we just can't account for because we can't see it. All the calculations describing the total mass of the universe imply that there's a whole lot more mass out there than we can see, than we can even detect. And we don't know where it is, we don't know what it looks like, and we don't know why we can't see it, but we're trying to find it. There's this idea of dark energy, that Einstein had this idea that there's actually a negative kinetic energy causing the universe to expand outwards. Then eventually, it may actually contract back in. It actually depends a lot on how much mass is in the universe. Eventually, maybe all the mass in the universe will pull itself back together from this expansion, and gravity will win over, and it will contract back in into a big crunch, and then maybe explode out again into another big bang, and maybe that's how universes form. We don't know. And so we're currently doing research trying to find this idea of dark energy and try to study it. And notice gravity is over here, because after all this time, we still don't get gravity. Remember, earlier in the year we talked about the string theorists. Maybe they know how gravity works. Maybe they know why gravity is so weak compared to the other fundamental interactions and why it seems to leak into the other 7 dimensions that we don't know where they are, but we don't really get gravity. Finding the Higgs boson was a really big step in that, but we still don't get it. And so the point I'm trying to make is that of all the stuff we know, there's still a lot more we don't. There are still mysteries to be explored and mysteries, hopefully, to be solved. And of course, this is the fundamental human condition, isn't it? I'm getting big here, right? These are big ideas. That this is why we do this. This is why we study physics, to try to answer the big questions. And hopefully this year has just whet your appetite. It's given you some inspiration, and it's given you the foundation that if you want to move on and study some of these things and maybe make a name for yourself, maybe contribute to our fundamental understanding, there's more to do. And so, we come to the end. You've made it to the end of AB Physics 1. Congratulations.